So this explanation of the photoelectric effect that Einstein just gave us is based on the idea that you can visualize light as a particle. But we've always been talking about light, its frequency, its wavelength, in terms of wave. So is light a particle or is it a wave? Well, Einstein said it was both. Einstein has both said that the light could be described both as a particle and a wave. This is referred to as the particle-wave duality, dual nature. It has two natures. It can be both particle or wave, depending on the context. And so let's talk about this for a little bit. Let's talk about why this is weird. If you really understand this, it's going to start to be kind of weird to you, because if we take, we don't tend to think of particles and waves as the same thing. We think of them as different things because they are. Let's take an example of a wave. The radio wave that we'll use, let's just imagine Waco's broadcast signal. It has a frequency, 103.1 megahertz. It has a wavelength which you could calculate. And it's delocalized, which means that it's spread out. It's not in one place. Well, what does that mean? Well, how would you find out whether Waco's radio broadcast signal was where you are? What? When you did what? Turn on a radio, right? You turn on a radio, turn to 103.1. If you hear white noise, then you know that the broadcast signal is not there. But if you hear a song, then you know that it is there, right? So where could I go to find a Waco radio signal? Could I find it in this room? Yeah. Yes. Could I find it in St. F? Yes. Could I find it in Vincennes? Probably, yeah. And what about Pinkstaff? Yeah, you can find all these different. So where is it? Where is it? The wave broadcast? It's everywhere. It's not everywhere, but it's spread out over a large area, right? And if I tried to weigh it, if I tried to weigh that signal, I probably wouldn't. What would you do? You got to scale out. Is that wave in this room? Yeah. If I put out a scale, will it register? No. What if I held the scale right under the broadcast tower? Would it weigh anything? No, probably not. So waves, electromagnetic waves, don't really have mass. And so why am I talking about this? Well, let's talk about something else that we would think of as a particle. The example I like to use is a Bratwurst. What is the frequency of a Bratwurst? How many cycles does a Bratwurst go through per second? It doesn't. It's a nonsense question. If you start asking this question, people will probably take away your freedom eventually, right? And what about the wavelength? We know the Bratwurst has a length, but it doesn't have a wavelength, does it? Like, how far does it go during a cycle? Bratwursts, I think we can all agree, are localized, right? They're localized. And localized, they're in one place. Delocalized means they're not in one place, they're spread out over a large area like waves are. And Bratwursts have mass. We could put a Bratwurst on a scale and it would read something. So what we can imagine now, remember what, does it even make sense to think about Bratwursts in the same way as we think about radio waves? No. Could you even begin to wrap your brain around the idea that they could somehow be the same sort of thing? You couldn't. But what did Einstein just say? He said light was both particle and wave. So does that make any sense? So let's try to think of a Bratwurst as a wave, shall we? Let's think of it. How does it work? How do you find the radio wave? You look for it, right? You turn on your radio here, you hear a signal. You turn on your radio in Pinkstaff, you hear a signal, right? You look for it. So let's look for a Bratwurst in the same way. Okay, what do? You look for it, you taste it, right? So you take a big old bite. Bratwurst. It just appeared in my mouth when I bit. Is that how Bratwursts work? We don't tend to think of Bratwursts don't tend to behave that way, do they? Similar. So Bratwurst, just what is the wavelength of a Bratwurst? How do you do this? It doesn't make any sense. Our brains should start shorting out when we try to think about it this way, because it just doesn't really make a lot of intuitive sense. But Einstein said we had to think about light in both of these ways. It can act like a wave, or it can act like a particle. So that leads us to a guy by the name of DeBroglie. DeBroglie, D-E-B-R, it's right there on the screen. DeBroglie came up with the idea that he said, well, Einstein showed that light is both a particle and a wave, but what's so special about light? He supposed that light wasn't really special. He supposed that everything is both particle and wave. Everything. In fact, he took Einstein's E equals mc squared equation and derived a relationship that is encapsulated in what is known as the DeBroglie equation, which is at the bottom of the screen. We'll show you in just a second. The DeBroglie equation is this. It says that the wavelength lambda of an object is equal to h. Now h I think we might have mentioned in passing before, but that is a constant. It's a very, very tiny number. Planck, it's named after Planck. It's Planck's constant, the guy who gave us the chunky energy, the quantized energy. That number is 6.626 times 10 to the negative 34th. It's small. It's a very, 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 very small number, unimaginably small. And what de Broglie said was that the wavelength of an object equaled that small number divided by mass divided by velocity. Now, what's weird about this equation? What's weird about this equation is this equation has a wavelength in it and a mass in it. Do we think of things as having both mass and wavelength? Do we think of a Bratwurst as having a wavelength? Bratwurst has a wavelength, or a mass, but not a wavelength. And a radio station signal has a wavelength, but not a mass. This is a formula. De Broglie gave us a formula that related things, masses, to their wavelengths. You could actually calculate the wavelength of a Bratwurst if you knew its mass and its velocity. There's the formula for it right there. And what ends up happening, though, is that h, this incredibly small number, because it's so incredibly small, we find that only very, very, very tiny things without mass, without much mass, exhibit wavelengths that are worth talking about. In other words, a Bratwurst, if you actually plugged in the numbers at relatively normal velocities, you would find that the wavelength number is nonsensically small. It's an incredibly small number. It doesn't even really make a whole lot of sense because large things don't act like waves. And that's the key to de Broglie. Mass tends to, the more massive an object is, the more it acts like a particle. And the less massive, the more it acts like a wave. So things that are incredibly, incredibly enormous, like you, tend to act like particles. Huge things like you or your mom or a mouse or a dust mite, those are all incredibly huge on the quantum scale, all act like particles. And things that are tiny, 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 tiny tend to act like waves. Like light photons would tend to act like waves most of the time. Things that are right in the middle, like electrons, get really confusing. So an electron sometimes will act like a particle, sometimes it will act like a wave because its mass is kind of right on the borderline. It's on the cusp between these two types of things. But they're not fundamentally different things. It's just that the more massive you are, the more you act like a particle. The less massive you are, the more you act like a wave. And that is just the beginning. Now I'm going to show you now is a good time to watch the Dr. Q quantum two-slit experiment, which is a really, really good next step that we can take in this quantum journey.